The final section of the prerequisite chapter, P.7, is titled Solving Inequalities Algebraically and Graphically. We're going to look at a few different types of inequalities, mainly absolute value and quadratic, and how we can solve those. And then we'll also do a little application at the end. We'll talk about projectile motion type problems. The first two examples are absolute value inequalities. I'd like to show you how to solve each of them algebraically without the use of technology and the graphing calculators, and then also kind of briefly, maybe real quick, show you what it would look like on the graphing calculators as well. Now with absolute value inequalities, there's two types that we're going to deal with. We need to know how to interpret the inequality, essentially. Whenever we have a less than or a less than or equal to, we can write a single combined compound inequality. Okay, so I'm going to write this like this. The x plus 5 is less than 12 and the x plus 5 is greater than negative 12. Notice that I stressed the word and. This is a compound inequality. It's like an and statement, compound inequality. Now when I solve this compound inequality, we subtract 5 off the middle. The result is negative 17 is less than x, which is less than 7. Or I want x's that are less than 7 but greater than negative 17. The answer looks like this. Now on a graphing calculator, I've already got it set up, so I'll just kind of show you real quick. Go to the y equals screen. There it is typed in. I've got each side of the inequality. I hit graph. I played with my windows a little bit, and what we see is the absolute value V-shaped graph, and we see the horizontal line 12 going across the screen. Let me real quickly recreate that on paper here for you. Okay, so there's my graph. We're just going to be real rudimentary here. I've got my absolute value graph. Looks like that. And I've got my 12. Looks like that. And what happens is these two graphs intersect at two places. They intersect right here. Well, that value happens to be the negative 17. And they intersect right here, which would happen to be the 7. So they intersect at the two places here that I've solved for. Now what I want to know is, where is the absolute value graph? Where is the V-shaped graph? Less than. So where is it? Think of it as under the line 12. Okay, if we look at the line right here that I drew at 12, you see that the graph is beneath it here, and it's above it kind of on the outside over here and over here. Well, where is it beneath the line 12? It's beneath the line 12 everywhere between these two intersection points. Everywhere between negative 17 and 7. Okay, so there's kind of the physical graphical interpretation of what we did algebraically. This next absolute value inequality, absolute value 3x plus 1, is greater than or equal to 2. Whenever we start with a greater than, this interprets as an or compound statement. An or compound inequality. If it is an or statement, then we have to write two inequalities to solve this type of problem. And so the two inequalities are going to be this. The first one is just as it is without absolute value bars. 3x plus 1 greater than or equal to 2. The other one 3x plus 1. We flip the inequality, less than or equal to, and we make the 2, or whatever number it is, equal to negative. Now we solve each of these. So this one, I'm going to skip writing the steps. 3x is greater than or equal to 1. Subtract it over. Divide by 3, we get x is greater than or equal to 1/3. Or over here, we get 3x is less than or equal to negative 3. Divide by 3, we get x is less than or equal to negative 1. Okay. So x is less than or equal to negative 1. Let's start there because it's the smaller values. Would be everything left of negative 1. Negative infinity, comma, negative 1. The other one is all the x's bigger than 1/3. Starting at 1/3, going to infinity. Now, seeing this on the graphing calculator screen might help make sense of that answer. I begin by typing it in. So there it is typed in, each side of the equation, or the inequality. I go to graph. I've done the little Z box to kind of zoom in on this. What we want on this particular problem, notice back here, we want every place where the V shape, the absolute value graph, is greater than 2. Everywhere where it's above 2. Okay, so I've got my V-shaped graph, I've got my horizontal line at 2, and everywhere that the V is above 2 would be everywhere to the right of this value. Okay, that value is the 1/3. And then everywhere to the left of this value, that value is the negative 1. So I do want the outside areas on this particular V shape, not the inside area. Next example, we'll go over how to solve a quadratic inequality. The first thing that we want to do when we solve a quadratic inequality is find the zeros. And typically I can find the zeros by factoring. So we have x times x makes the x squared. We'll go with -4 minus 1. So we have 0 at x equals 4 and x equals 1. Now that's enough for me to kind of get an idea of what this graph would look like. If I graph this without the graphing calculator. Okay, well we just found out at 1 and 4, the zeros, this is where the graph crosses through the x-axis. So it looks something like this. I know its shape is a parabola because it's x squared. I know it goes up because it's positive x squared. We've all seen enough of these to kind of know what their general shape looks like. And what I want to know, we'll just use the graph to answer this. What I want to know is, where is the graph of the parabola? Where is the graph of this equation less than 0? In other words, where is it under the x-axis? Well, it's under the x-axis right here. It's under the x-axis between 1 and 4. Okay? If you pretend like this is a number line right here, the x-axis is a number line, you've got circles on 1 and 4 and you're shading on the number line. We're shading everywhere between 1 and 4. And there's my solution. Rounded parentheses because we are not equal to. Next example is another quadratic inequality. We're going to solve it the same way. I'm going to begin by finding the zeros, which will require that I factor this. So 2x times x makes my x 2x squared. I think I'm going to need a plus 3 here because that'll make 6. And a plus 1 here, as 6 plus 1 makes the 7. And 3 times 1 is 3. So I get zeros at x equals -½ and x equals -3. Okay, so the graph of this parabola would look something like this. It's going to cross through the x-axis over here on the left-hand side. Crosses through the x-axis right here at -3 and right here at -half. Okay, so what I want to know then is where is the graph of this parabola, okay, the U-shaped graph that I have here, where is it greater than 0? Where is it above the x-axis? Well, it's above the x-axis everywhere out here. Everywhere to the right of -1/2, and it's above the x-axis everywhere out here. Everywhere left of -3. So I want to write my solutions as those two sets. I want everything from -infinity to -3 and -half to infinity.